All right, you guys, let's look at the last section of chapter 6. It's dealing with the applications we need to know how to do. Now, I already talked about these, when we were meeting, all 7 of us or whatever, but it involves 2 different kinds of application problems, at least the ones I picked out. One is rate of work, which is the subject of this video, and the second one is about rate times time equals distance again, with a twist, okay? So we talked about it. Doesn't mean you watched it, but you should watch the Zoom lectures as well. But this particular one is basically the rate of work problem. I'm going to give you an example up here. I think I'll start that way. So suppose that Jim takes, I don't know, 30 hours to, I don't know, paint the building. But then Sally takes, I don't know, 50 hours, she's meticulous, to paint the building. The question is going to be, how long does it take them working together? Working together. How long will it take if they work together? And I got another one down here as well that we're going to talk about Jen and Morris. We'll do that problem, but I just wanted to invent a problem like this and show you the mechanics of it. First of all, if Jim takes 30 hours and someone helps him, you'd think it's going to take less than 30 hours, right? Otherwise, don't help me. But so it's going to take less. So the first thing you're going to figure, it's going to take less time than Jim. He's fast, and it's going to be even faster with Sally helping him. Here's the thing about the mechanics of this. If they work, say they worked 6 hours, how much have they got done? Well, Jim takes normally 30 hours, so when 30 hours is up, he's done with the job. So if he only works 6 hours, then you look at it as he did 6/30ths of the job. That makes sense? He still has to go 24 more hours to finish. For Sally, it's 6/50ths, which is even smaller a portion of the job. And if they're working together, you add those 2 together. When are they done? By himself, Jim would be done if he went 30 hours, so that would be 30 over 30, and you'd have 1. But if you add these fractions together, if I were to add 6/30ths and 6/50ths together, I'm not going to get 1. But what we do is we force it equal to 1, and we change that 6 to some variable x, and you'll force x to be the magic number that is the time it takes for them to finish. And what I did right there is I'm showing you how I set up all these problems. And the way it is done is, well, I'll cheat and I'll show you way down here on the next page this kind of a formula. And we're going to do 3 of them, and this is going to be kind of a lengthier kind of video, hopefully not too bad. The setup is not terrible. Okay, so we shouldn't be shuddering when we see these problems. You should look at these and go, I'm going to get these ones down. So let's read this next problem. Jen can fill the condiment dispensers at a restaurant in 25 minutes by herself. Morris can do the same job in 35 minutes by himself. So the numbers are important. Jen, 25, Morris, 35. How long would it take them to do the job if they work together? Here's what you do. You just go x equals time it takes for them to do the job working together. To do the job working together. Isn't that what they asked? I have a thing about teaching word problems to algebra students, which is you just look at the question and you repeat it, but with a variable. How long will it take them working together? It'll take them x. What is x? I'm thinking, since they talked minutes, do you see this? And minutes, x is going to be also minutes when we get the answer. So I'm going to follow that. I'm going to say Jen worked x minutes, and I'm going to say over her time, which is 25. So x out of 25 minutes. If she were working by herself, she'd have to go 25 minutes. 25 over 25 equals 1 job done. But she's being helped by Morris. He's working the same amount of time, and he is 35 minutes. He's slower, okay? But then you set the whole thing equal to 1, and I like to say 1 means done. Right? And these notes are on the next page, I think. But this is the setup for solving a rate of work problem. The X represents how many minutes they were working. X is going to be something less than 25, because if X is 25 right there, you already have 1. Okay, so it's going to be less because you're actually adding some more. So regardless, what we're going to do is we're going to solve this thing. I'll put this in black now. I'll go. So we're going to solve for X. That's it. And then I was showing people in class what I do is I go, here we go. We're going to clear the fractions by multiplying everybody by something to make them clear. You can wrestle. Yes, you can. You can wrestle with finding the LCD of 25 and 35. But what I was saying was, it's easier to just go, why don't we just keep it as 25 times 35. And when I multiply through, it's going to cancel those boys. And then 25 times 35 here. What I mean by that is, let me write this out. 25 times 35 times the first guy over here on this side times the second guy, you know what I'm saying? And over here equals one more 25 times 35 over 1. And what we're doing is we're clearing the fractions. As you guys getting through that homework in the previous section, this should be kind of a minor cakewalk to you guys, because you take out that green marker and you start canceling. The 25 cancels. Who's left? 35x. The 35's cancel. Who's left? Plus 25x equals nothing cancels. 25 times 35. Okay, I guess I'll get my calculator out, right? So, let's see. 25 times 35 is 875. Okay, but we're also collecting these guys. These two combine to make 60x, and over here I said 875, so that when we divide and get an answer, we take that, divide by 60, and it's a pretty rough looking number. It's 14 whatever. But, in this case, I might round off. And what I really have is 14.58 and then 333 forever, whatever that is. You want to change it to a fraction? I will. I'll hit that magic button on the calculator if I can find it. There you are. And it's saying 14 and 7/12 equals 14 and 7/12 minutes. That's the answer. Now, look at your problem. Does it make sense? Jen by herself, 25 minutes. With help from Morris, less than 15 minutes. Makes sense, doesn't it? Let's try another one. On the next page, I'm actually explaining this right here. Jen time that she worked, divide by how long it takes her. Plus time Morris worked, divide by how long it takes him to finish the job. And 1 means done, okay? Now on this one, I said try setting this one up. The twist is there's 3 workers instead of 2, but it's an extension of what we just did. So if you want to pause it, work on it, and then watch the video later, okay? 1, 2, 3, pause. So then you come back and you go, there's Julio, there's Margie and Joe. They're working at Dodger Stadium. Julio takes 20 minutes to drag the infield. Those guys are walking along and they're dragging that, I don't know if you're a baseball fan, but they're dragging this thing that makes the infield really smooth. Okay, it's a silly thing. At 7th inning, they do it, and it's a race or something. Anyway, 20 minutes to drag the infield. Margie, 15. Joe, 10. Joe's been there a while, or maybe he's new. I don't know, and he doesn't do it right. But anyway, how long will it take them if they do it all together without running into each other? You just do this. There's Julio plus, I think of it as fractions. Julio's, let me write that better. Julio's fraction of the job done plus Margie's fraction and plus Joe's fraction. If you add them all up, you're done when you reach 1. So Julio's fraction, all of them are, I don't know how long they were working together, so they all get an X upstairs. but then you put their speeds down below them. So Julio's is 20, Margie's is 15, and Joe's is 10. Okay? And this is what we're doing. There's your equation. Pretty quick setup, I'm telling you. Then I do this thing where, okay, now I'm solving this thing, okay, and I'm going to multiply both sides by, you know what, if you want to figure out 60, that's pretty easy. You can figure out 60, you know. But if I do it the other way, I just go, well, there's a 20 and a 15, and I'm so lazy, I don't want to figure out 60, so 20 and 15 and 10. You know why? Because I have a calculator. And when I distribute, I'm going to do this one without writing it 3 or 4 times. I'm just going to simply say the first guy is going to lose the 20, and it's going to leave behind 15 times 10 times x, plus the second guy loses the 15, and it's leaving 20 times 10 times x. Last one loses the 10, and it's 20 times 15 times x, and on the other side is nothing. It's just 20 times 15 times 10. All right, let's do some math, and we maybe grab that calculator. We got 150x plus 200x plus 300x is equal to this product, which I'm not gonna mess around. I'm just gonna do it. So it's gonna be, well, actually it's 200 times, oh my gosh, I'm gonna do it all in my head. I don't want to. 20 times 15 times 10 is 3,000. Okay. Big deal, big numbers, but I have a calculator. Combine these two, all the three of those terms, 500, 650, x is 3,000. You ready for the answer? You're going to divide by 650, divide by 650, and let's see what we got. So I have 3,000 divided by 650 is 4.615, etc. 4.615, But if I change it to a fraction, which looks better, I think, I've got 4 and 8/13. It equals 4 and 8/13. And then you look for the time. Minutes again, minutes. If they're all buzzing, all three of them, it takes them less than 5 minutes to finish the job. Hopefully they don't run into each other. Okay, I got one more to show you here, and it's very similar. So you can pause and stare at that, but that's the answer. And this is the last one. It says, sometimes things work against us. In this case, an inlet pipe can fill an empty tank in 5 hours, but the drain pipe takes 7 hours to empty it. How long will it take to fill the tank if the pipe begins to fill it, but the drain is left open? So it goes something like this. The inlet pipe's fraction. Then there's the drains or drain pipes fraction, and we're still trying to get to 1. Here's the rub. You ready? Since the drain is taking stuff away, the inlet pipe adds a fraction towards the tank, but then the drain takes it away, and we subtract. We subtract because the drain, someone left the drain open. What'd you do that for? I don't know. It was funny. Not funny. So these guys still, though, they have a numerator of x. That's the time they're running, but the inlet pipe, 5 hours, the drain, 7. There's your setup. You know what I'm saying? This is pretty good stuff. We take this guy and we multiply both sides by, well, Mr. Lazy says, why don't you just do 5 times 7? That'll do the trick, 5 times 7. Pretty cool. I mean, to be able to do this, we distribute, you lose the 5, but you still have the 7, minus, lose the 7, but you still have the 5. Don't forget those x's. And over here you have 35. So then you have 2x is 35. So x, when you divide, you know what I'm going to do. I'm so lazy. 35 divided by 2 is 17.5. So 17.5 hours this time. Hours, right? To finish this off. So someone's put the drain on and boy, it's taken a long time to fill. It usually gets done in 5 hours. What's wrong? Oh, so-and-so left the drain open. That's why it's taking longer. That's it. Those are the rate of work problems you really want to study and master because they're really kind of straightforward. Thanks for listening. And next stop will be the other type of problem. See ya.